Good morning, students. In this session, we will continue with the topics electron gain enthalpy followed by electronegativity. Electron gain enthalpy means it is nothing but enthalpy, energy change. Energy change accompanied during addition of an electron to an isolated gaseous neutral atom in its ground state. What is the electron gain enthalpy or first electron gain enthalpy? Electron gain enthalpy, or it is also called as first electron gain enthalpy. Both are same. So, what does it mean? Energy change accompanied. Energy change means it may be released energy or absorbed energy. So, energy change accompanied during addition of an electron to an isolated gaseous neutral atom in its ground state is called as its electron gain enthalpy or first electron gain enthalpy. Energy change accompanied means it may be released energy or absorbed energy. See, in case of elements, all elements except zero group, except that of zero group, nitrogen and 2A group elements. What are 2A group elements called as? Alkaline earth metals. In case of all elements except that of zero group, nitrogen and 2A, energy is released. During addition of electrons. Suppose M is an atom, gaseous neutral atom in its ground state, to which when an electron is added to give uni-negative gaseous ion. This is a uni-negative gaseous ion. Energy released is called as electron gain enthalpy. As it is exothermic in nature, it is given in negative terminology. Okay. Now, whereas for noble gases, nitrogen and 2A group elements, when an electron is added to an isolated gaseous neutral atom to give a uni-negative ion, energy is absorbed. That reaction is exothermic, whose sign is given with a plus. Okay, it is positive. So, for electron gain enthalpy for noble gases, nitrogen and alkaline metals was noticed as positive, whereas electron gain enthalpy for all elements other than those three observed as negative, exothermic in nature. See, here we need to remember why it is positive. We need to understand. See, in case of noble gas, already suppose if you take helium or neon or argon, whatever it is, all noble gases have completely filled set of outer shell, and it is more stable, more symmetric in nature. It is stable with respect to the completely filled stable electronic configuration. See, half filled or whatever it is gives, half filled or completely filled electronic configuration gives stability because of symmetry in the distribution. Because of that reason, noble gases are said to be having stable configuration. See, now if an extra electron is added to this, what happens? That electron will be added to the next shell, which leads to an unstable configuration. That is why it will not allow the addition of an electron. Absorption of energy is required to add an electron to an isolated gaseous neutral atom of noble gases or nitrogen or alkaline earth metals. Even in nitrogen also it is already half filled in configuration, right. So, it will not allow the addition easily. So, even in alkaline earth metals also they have NS2 configuration, beryllium, magnesium, calcium, strontium, barium and radium. They have completely paired NS2 configuration. If an electron is added, they are losing that stability. That is why in case of these three means noble gaseous elements and nitrogen and alkaline earth metals, electron gain enthalpy or first electron gain enthalpy is observed as positive. In rest all cases, first electron gain enthalpy is observed as negative. Now, here one more point we have to notice. Earlier, this electron gain enthalpy was also termed as electron affinity. Okay. Affinity means its affinity to gain an electron, affinity to gain an electron. So, if electron gain enthalpy is negative, it is said to be having positive electron affinity. What does it mean? Energy is getting released during addition of an electron in case of a particular element, means that element is more prone to gain an electron, means its affinity to gain electron is positive, it has a positive affinity to gain an electron. That is the notation you have to follow. Similarly, if electron gain enthalpy is given as positive, it means its electron affinity is negative, means it has a negative affinity of gaining electron. In that sense, okay, energy value may be same, but the sign varies here and there. You have to notice that point. And next is this is all about first electron gain enthalpy. When it comes to second electron gain enthalpy, what is the meaning of second electron gain enthalpy? See, we have formed a uni-negative gaseous ion. Now, if I want to add one more electron to this, uni-negative ion to make M-2, what is the change accompanied? Energy is getting released or absorbed. Energy will be released or absorbed. Usually we expect energy to release in a similar manner, right? But here what happens, already there is much electron density. Electron density is high. Because of high electron density, there exist interelectronic repulsions already in a uni-negative ion. Yes or no? In that situation, when an extra electron is added, will they allow? Will the repulsions allow the extra electron to get added? No. That is why addition of one more electron to a uni-negative ion is not an easy process. Instead of releasing energy or more than the released energy, expected release of energy, this has to absorb energy to get added into uni-negative ion. That is why addition of electron to a uni-negative ion is always positive. Means this energy change accompanied during addition of an extra electron, second electron to a uni-negative ion is called as second electron affinity. What is the definition of second electron affinity? Energy change accompanied during addition of an electron. I am repeating, energy change accompanied during addition of an electron to a uni-negative ion is called as second electron affinity. Usually, in all cases, second electron affinity is absorbed only, it is endothermic only. Second electron affinity is always endothermic, means energy is to be absorbed rather than released, because to minimize the repulsions from the existing electron density. Second electron affinity is always endothermic. So, it is always with a positive sign. Understood? Now, what are the factors that influence this electron affinity? What are the factors? Electron affinity is inversely proportional to atomic radius. Smaller the size, more is its electron affinity. Obviously, when the size is small, nuclear influence is more. So, smaller the size, more is the electron affinity, means more means electron gain enthalpy. That is a better notation. Electron gain enthalpy is more when the size is small. Similarly, electron gain enthalpy is also inversely proportional to inverse or direct nuclear charge. You take nuclear charge, directly proportional to nuclear charge. Electron gain enthalpy is directly proportional to nuclear charge, because more the nuclear charge, more is the attraction. More the nuclear charge, more is the attraction. So, more the nuclear charge, more is its electron gain enthalpy. Smaller the size, more is the electron gain enthalpy. And electron gain enthalpy is also inversely proportional to shielding effect. Shielding effect is more, means it cannot gain electron easily, no. So, its electron gain enthalpy will be less. So, these are the factors that influence this electron gain enthalpy. Already we discussed the terminology electron affinity also. For example, fluorine gaseous atom, when an electron is added to give F minus gaseous ion, electron gain enthalpy is observed as minus 328 kilojoules per mole. It is usually expressed in kilojoules per mole, even ionization enthalpy also expressed in kilojoules per mole, right. Now, this is electron gain enthalpy. Now, for the same reaction to give uni negative F minus, electron affinity is plus 328 kilojoules per mole. This is what the notation one has to remember. Okay. Now, suppose you consider some element nitrogen. Nitrogen plus electron gives rise to N minus. Suppose if delta H electron gain enthalpy is plus 31. I have already given for nitrogen, alkaline earth metal and noble gases, first electron gain enthalpy is positive. Electron gain in the rough value I am giving. Then for the same equation, N minus gas, electron affinity is given as minus 31. So, a rough value I had given, these values are accurate. Okay. So, in this way, to avoid confusion, always we have to discuss in terms of both the terminologies, electron gain enthalpy and electron affinity. Usually, electron gain enthalpy is a proper terminology. In case of a negative electron gain enthalpy, means if it is exothermic, it means that element's electron affinity is positive. Okay. Now, let us see the trends of electron gain enthalpy across a period and down the group with the help of these factors. When it comes to the trends of electron gain enthalpy across a period and down the group, so this is also depending on atomic radius only. Across a period, how atomic radius varies from left to right, atomic radius 1, 2, 3, 4, 5, 6, 7. See, in any given period, alkali metal is of large size and halogen is of, means 17th group element is of small size. Size of 0 group element is slightly greater, because for them we are following non-bonding radius, which is obviously greater than the bonding radius. Now, as electron gain enthalpy is electron gain enthalpy, delta H electron gain enthalpy is inversely proportional to atomic size. As the size decreases, electron gain enthalpy increases. So, as atomic radius decreases, electron gain enthalpy increases. So, in any given period, larger size will be from alkali metal. So, larger the size, less is the electron gain enthalpy. Less electron gain enthalpy is by alkali metal, is shown by alkali metal, and high electron gain enthalpy in terms of released energy. High electron gain enthalpy is shown by or is possessed by 17th group element. 17th group element, that is halogens, fluorine, chlorine, bromine, iodine in any group. And electron gain enthalpy of 0 group elements, electron gain enthalpy of 0 group elements is positive, because of an electron is getting added to the new shell, it leads to an unstable electronic configuration. That is why it is not a spontaneous process. It needs to absorb, electron need to absorb energy to get added to an isolated gaseous noble gaseous element. Now, when it comes to the trend down the group, trend of electron affinity down the group. So, as atomic radius increases down the group, so with increase in atomic size, electron gain enthalpy, decreases. So, in any given group, first one will be usually of a high electron gain enthalpy and last one will be of low electron gain enthalpy, right. But there are some exceptions in this. What are those exceptions? In case of halogens, first one is halogens. In case of halogens, we have fluorine, chlorine, bromine, iodine. Fluorine, chlorine, bromine and iodine. We expect which element to have high electron gain enthalpy? Smaller the size, more is the electron gain enthalpy. We expect fluorine to be with the high electron gain enthalpy. But because of small size, what happens in fluorine? In fluorine, there exist interelectronic repulsions because of its small atomic radius. Already existing electrons itself will repel with one another, and these interelectronic repulsions won't allow the newly added electron to enter. Understood? Interelectronic repulsions won't allow the newly added electron to enter in an easy manner. That is why even though it is smaller, it is not the one with high electron gain enthalpy. So, high electron gain enthalpy is shown by chlorine. Because of small size, there exist interelectronic repulsions, of which this is the symbol for there exist, of which electron gain enthalpy of chlorine is greater than that of fluorine. So, among all elements of the periodic table, 17th group elements are the one that shows highest electron gain enthalpy in any given period corresponding 17th group. Among 17th group elements, instead of the expected smaller one, high electron gain enthalpy is shown by chlorine. So, electron gain enthalpy of chlorine greater than fluorine greater than bromine greater than iodine. This is the sequence. Similarly, the previous member also. Similarly, what is the previous group of halogen? 16th group, oxygen, sulfur, selenium, tellurium and polonium. Anyhow, this is a radioactive element, right? We need not study, means these properties, chemical properties were not studied completely. Now, among these also usually oxygen, sulfur, selenium and tellurium. Oxygen is the smaller one, of course. So, one expect oxygen to have high electron gain enthalpy, yes or no? But because of the same reason, because of the same small size, there exist interelectronic repulsions even in oxygen also, of which high electron gain enthalpy is shown by sulfur. Sulfur greater than, selenium greater than, tellurium greater than oxygen. Oxygen, in case of oxygen, such a less amount of energy is released. Okay. Now, let us discuss about the second electron affinity or second electron gain enthalpy cases. Now, when it comes to a question on second electron affinity, see which of the following reactions are exothermic? First electron affinity of fluorine, oxygen, chlorine. First electron affinity of fluorine is always exothermic. Even oxygen is also exothermic. Even chlorine is also exothermic. Just now we discussed their trends also. What about this fourth equation? It is O minus plus electron. Second electron affinity is always endothermic. So, which of the following reactions are exothermic? Means A, B and C are exothermic, whereas the last one is delta H is positive. This is endothermic reaction. So, this is one type of question possible on electron gain enthalpies. Another question is arrange oxygen, sulfur, fluorine and chlorine in decreasing electron gain enthalpy values. Sir, shall we remember the values? You need not remember any value, don't worry. Just arrange them in decreasing electron gain enthalpy sequence. So, among fluorine and chlorine, which possess high electron gain enthalpy? Chlorine. Among oxygen and sulfur, which possess high? Sulfur. So, electron gain enthalpy of chlorine is greater than fluorine. Among sulfur and fluorine is more prone to gain electrons. That is why you can notice the numerical values in textbook also. So, chlorine greater than fluorine, greater than sulfur, greater than oxygen. This sort of questions are also possible for objective examinations. Anyhow, this is only for the PU based program. So, we are limiting our this one as per the time constraints also, and there are so many higher applications of this electron gain enthalpy or electron affinity which we will discuss in JEE and NEET and advanced classes. When it comes to the next subtopic, that is electronegativity. Electronegativity, it is the tendency of an atom or ability of an atom to attract the shared pair of electrons more towards itself. Okay. See, it is not a measurable property, it is different from ionization enthalpy as well as electron gain enthalpy. Electronegativity is tendency of an atom, it is just a tendency of an atom to attract the shared pair of electrons. See, it is a property shown after bond formation, to attract the shared pair of electrons more towards itself. That is it. It is just ability to attract more towards itself. The shared electrons are more attracted, not gained. There is no gaining phenomena here. tendency of an atom to attract the shared pair of electrons more towards itself is said to be electronegativity, right. Now, usually this electronegativity is inversely proportional to atomic radius. Smaller the size, more is the nuclear influence, obviously, right. This electronegativity calculation was well explained by Pauling in his Pauling scale, which was later explained in a more satisfactory manner by Mulliken's scale. Even Allred-Rochow scale is also there, Allred-Rochow scale. But still we are following now, even now also we are following the electronegativity values calculated with respect to Pauling scale. Using Pauling scale, electronegativity value of fluorine was observed as 4.0, oxygen was noticed as 3.5, nitrogen and chlorine was noticed as 3.0, hydrogen was calculated as 2.1, etc. Better you remember some electronegativity values so that you can answer some questions with more ease, right. Now, when it comes to the trends of electronegativity, as electronegativity is inversely proportional to atomic size. Across a period, how the size varies? Across a period, how the atomic size is varying? Across a period, size is decreasing. As atomic size decreases, as atomic radius decreases, electronegativity increases. As it is a phenomena shown after bond formation, we can neglect noble gases 1A, 2A, 3A, 4A, 5A, 6A, 7A. This is 17th group, 7A group elements, halogens. Okay. Now, in any given period, high electronegativity is shown by 17th group element, and low electronegativity is shown by 1A group element, alkali metals. Okay. Like this we have to remember. Now, down the group how this electronegativity is varying. So, with increase in atomic size, as atomic size or atomic radius increases down the group, electronegativity decreases. Of course, there are some exceptions, namely boron family and carbon family. There are some exceptional variations in the trend of electronegativity. That is all due to lanthanide contraction consequence and effects in this one, actinide contraction and lanthanide contraction. But in general, in most of the groups, this trend is followed. So, as down the group atomic size increases, electronegativity decreases. So, here which is most electronegative element? Already we calculated this one, fluorine as the most electronegative element. One more phenomena we have to study. See, this electronegativity is a measure of metallic and non-metallic character also. So, non-metallic character is directly proportional to electronegativity. More the electronegativity, more is the non-metallic character, and metallic character is inversely proportional to electronegativity. Less the electronegativity, more is metallic character. So, across a period in the total periodic table, left to right electronegativity increases, top to bottom electronegativity decreases. Top to bottom. Okay. You have to prepare some shortcut diagrams in this way for all these periodic properties. In our next session, we will discuss the rest of the periodic properties, right.